Okay, welcome back to Machine Learning Compilation. Hello, everyone. In the last week, we started our first lecture and giving an overview of the overall process of machine learning compilation. In this lecture, we're going to talk about a particular component in the machine learning compilation process, which is called Tensor Program Abstraction. Okay, let's begin. So here's the overall outline of today's lecture. To recap, in the first lecture, we talked about what are the key elements in machine learning compilation. First of all, there is multi-dimensional tensor or multi-dimensional arrays that help us to store the input, output, and intermediate results of model executions. And then tensor function encodes the computations among the input and output. And these two are really key elements that encapsulate the process of machine learning compilation. A lot of the optimizations in MLC is about how can we take a set of tensor functions, transform them, and getting more optimized ones to be able to help us to get either more optimizations, minimize dependencies, and solve other goals that we have in MLC. Among those set of tensor functions, one of the things we're going to look closer today is what we call a primitive step. So when we're executing a neural network or machine learning executions, it usually involves several steps. For example, in this particular example of a two-layer neural network, we have the first linear layer that then followed by a bias add through a nonlinear activation function, another linear layer, and a softmax. So it contains really several steps. A successful machine learning framework will be able to interrogate implementations from different parts and being able to execute that model execution end-to-end. However, one of the very important components here is how do we implement this specific step? For example, how do we implement a specific add function here? And this particular element is called primitive tensor functions or primitive function. In certain cases, people call them tensor operators. And usually these are tensor functions that correspond to a single unit of computation if we look at it from this kind of end-to-end view. Of course, there can be more detailed implementation of this particular primitive function, but from this global neural network or machine learning model execution point of view, this operation is kind of primitive. So our question here today is, again, coming back to the key elements of machine learning compilation and the idea of abstraction and implementations. The question we want to have today is, what are possible ways for us to represent a primitive tensor function, and what are the possible ways that we can use to optimize a primitive tensor function? Okay. So just like we talked about in the last lecture, the primitive tensor functions appears in both in MLC process, and in a lot of cases it also appears in common machine learning frameworks. For example, in that particular case of a length 128, we could do something like getting two PyTorch tensor together and then call a torch.add function. So in this case, torch and add can be viewed as a primitive tensor function in a PyTorch length. Of course, under the hood, torch.add is a bit more complicated. That also still handles things like output memory allocations, type conversions, and so on. But in this particular usage, we are trying to restrict it so that we are only calling it for an input array of length 128 and 128. We're going to store that directly onto output array that is previously pre-allocated. So a question that we have, of course, torch.add itself is a way to represent a primitive function. What are the other ways we can use to represent a primitive function? So this comes back to our conversation, right, in terms of abstraction and implementations. In the last lecture, we talked about the abstraction refers to different ways we can use to implement the same system interface. So for a primitive function like add, we can implement in ways like torch.add, which is kind of like one way to directly represent that as a call onto a library function, which then get dispatched onto some of the underlying implementations of that addition function. Of course, we can also directly express a set of operations we need to perform in order to realize this addition function. So for example, in this particular case, we could write it out just like a Python code that expresses, hey, in order to compute this array computations, we are going to do a for loop over a range 128, and we are going to, do this addition functions based on the iterator that we have on that. Or more commonly, actually, there will be usually those operators are implemented in more like a highly optimized low-level primitives, and those low-level primitives can be implemented in either, for example, C language or sometimes assembly language. So you might want to, try to implement this using a C function. So at least, in this particular slide, we already get 3 ways to implement the same tensor operator function or tensor primitive function that adds the true vector of length 128. And, they are different abstractions, right? So in this case, on the left-hand side, torch add is just a symbolic placeholder that says, I'm going to call torch add function. In the middle, it's a Python function that represents the computations that we have in here. And on the right, you can view the C as another kind of abstraction we use to represent the primitive functions. So the question that we have and want to keep in mind is, as a part of MLC process, which abstraction we want to choose to represent primitive functions, and how do we do effective transformations among those? Okay, but okay, now assume that we have an abstraction for primitive functions. What can we do with those abstractions? What are the typical MLC processes that are involved in using those primitive functions? So a common way to involve primitive function transformation in MLC is simply, you take in deployment form of machine learning model executions that contains a specific primitive function, and you try to map that onto another one. For example, one possible optimization or possible transformation we can do is, say, on the left-hand side, this is addition function that is written in a plain for loop, and we're going to transform it onto the right-hand side. Of course, this is a pseudo code. It's not exactly the code that you will expect to write in Python, but just to give a high-level idea, what it means is that we're going to parallelize this outer loop, hopefully through using multiple calls, and then we're also going to do those addition computations in a unit of 4. So the idea is that if I have a vector that contains 128 elements, what we're going to do is we're going to divide it into pieces where each of it contains 4 elements, and each computation in here will try to load in 4 elements from A and another 4 element from B. I'm going to use this function to perform addition of that 4 element in a single shot, right? So in that sense, the primitive function implementation on the right-hand side is certainly can be more efficient than the primitive function implementation on the left-hand side. So in a lot of cases, many machine learning frameworks offers you is the ability to be able to look at the primitive functions that we are using in our machine learning executions and try to dispatch that, or try to directly translate them onto more optimized ones based on the target environment of interest. For example, if we are looking at environment like CUDA environment, maybe what we want to do is we want to call into libraries. If we are looking at a CPU environment like ARM, maybe we want to make use of things like a vector instruction, like a neo instruction that are native to the ARM platform. Okay, so this is primitive function transformation is kind of like I would say one of the most straightforward transformations that we will apply in an MLC process. One interesting thing that you can find is that in this particular case, the only difference between the left-hand side and right-hand side are this realization of the addition function, assuming that all the rest are the same. for the purpose of the of this particular example. Because of that, what we need to do is we just need to pay attention on these primitive functions themselves. So I don't need to worry about the overall execution, because effectively, as long as they present the same interface, hopefully they can be incorporated in the same overall execution process. So what we can do here is we can look at the primitive function transformations alone, independent from the overall end-to-end computation. Remember that this is not the case for all the MLC transformations. In the future, we'll talk about transformation like operator fusion. That's going to involve both the changes on the primitive function side as well as the changes on the overall execution side. But for the purpose of today's lecture and for the purpose of particular transformations, we just need to think about how can we take a primitive function and effectively transform it to a more optimized version. There are different approaches that most frameworks and MLC system takes. Of course, the easiest way that we can do here is to simply remap it to library calls. For example, if we are doing add in a CUDA environment, what we're going to do is we're not going to write out this for loop. So effectively, there's no this for loop. You just get originally at your high level, you will know that this is the add function. And what you are going to do is you are going to directly map that onto a CUDA function, which we can implement in CUDA, or or you can directly invoke the native libraries that implement that effectively. This is the most common approach in most of machine learning frameworks, and this is still a very important one that ensures that we get good overall efficiencies. And we'll discuss that in the incoming lectures as well. On the other hand, besides this kind of a call string mapping that you want to detect, hey, here's a bulk CUDA or bulk add operator, you move that onto a CUDA add operators. We also want to do more fine-grained program transformations, which, in this case, assuming that the original program can be written as a for loop, how effectively can we find a way to transform that onto possibly more optimized implementation? And remember that depending on the approaches, whether you are doing simple library mapping or fine-grained transformations, there's a consequence in terms of kind of abstractions that we are going to use. For example, if we only care about library call mapping, the abstraction we can use for these machine learning executions can stay at a relatively high level. We just need to know that this is add, and you don't need to unbox that to say, hey, here's the loop in here. But if we want to be able to do more fine-grained transformations, like we want to be able to start from a loop and transform that onto this parallel for implementation, then we will need a different kind of abstraction. Of course, one might ask, why do we need more fine-grained transformations? This is because there are always trade-offs in terms of complexity. For example, if we are going to simply map everything to library calls, then we will need to create that mapping for every high-level primitive functions to every platform target, and a lot of those have to be manually implemented, which consumes a lot of resources. But if we do more fine-grained transformations, maybe we will find out that the transformation for add is similar to the transformation for, say, a subtraction, so that we can reuse that approach to be able to optimize more tensor primitive functions as much as possible. Okay, so that's the general motivation on why we might need different kind of abstractions for fine-grained primitive function transformation. Okay, so hopefully right now we kind of understand what is a primitive function is, and there's the need of being able to transform between implementation of primitive functions. Next, we're going to talk about an abstraction for tensor primitive function, which is the Tensor Program Abstraction. So specifically, a Tensor Program Abstraction focuses on transforming the loops transforming the loops and layout of possibly fused primitive operators. And so this is a code that expresses the possible tensor program for these vector additions of 128. So this is an example program instance in TVM framework. There are a few key features that a typical tensor program will exhibit. So first of all, there are three key elements in here. First of all, the tensor program usually contains a multi-dimensional input and output buffers. In this case, it only contains input and output buffer for the input and output. On the other hand, in a lot of cases, we can also have temporal buffers that hold the intermediate results. The second element of the tensor program is that it will usually have a loop nest that tries to iterate over multiple dimensions and trying to derive the compute iterations across these multiple dimensions. And finally, for the given loop, there will be corresponding compute statement that runs the corresponding computation. These are like three key common elements of a tensor program. Of course, this particular example is in TVM, which is one of the machine learning compilation framework. Depending on which framework you are going to look at, or the approach a specific platform might take, the specific tensor program abstraction might look slightly different. However, all the three key elements are always here. So we're looking at loop nest computations and multi-dimensional buffers. So of course, in this particular case, we are looking at one dimension, so it's a single dimensional buffer. But we could imagine that we can also do additions for two-dimensional matrix or three-dimensional tensor as well. Okay, so once we have a tensor program abstraction, one of the things we want to think about is what can we do with it? So why do we need a tensor program abstraction as opposed to simply express it as a high-level primitive, like just playing at? Or another question we can ask is, what if we just directly use lower level code as an abstraction for a primitive tensor program? For example, I could directly say use a C program or CUDA program to express the same tensor program computation. Is that possible? The answer is it depends. In a lot of cases, the answer is maybe. Because remember, our overall goal here is not only to be able to represent a primitive tensor function, we also want to be able to effectively do transformations among them. Of course, for example, if my implementation is a low-level C program, we will be able to take that low-level C program for one variant of implementations, and we can, of course, go and implement another variant, but that will cost additional engineering. So the question is, can we actually leverage some information and do effective program transformations to be able to get a more optimized version? So we're going to do very soon in the next slide. So why do we need a tensor program abstraction? So the key here is, we want to be able to carefully design the tensor program abstraction that enable us to be able to do what we call program-based transformation. So instead of having developers to manually write like one form of code on the left-hand side and then another code on the right-hand side, we want to be able to have a way for us to explore possible program optimization so that for our initial state, we can apply some program-based transformation, which we'll explain in the next few slides, so that we can take an initial state, you want to apply the transformation, and eventually we'll get to the other state. And I want to do that using program rather than having another engineer and go and craft this additional part, because there could be a lot of possible implementations of the primitive function, and our goal is actually go and find a relatively optimized one and supply that. I want to be able to explore that possible space of primitive programs in this case. And one of the key things here is we want to be able to carefully design the abstraction so that it helps us to do this kind of transformation. But before talking about the key points in abstraction, let's dive into possible examples we can do. Like, what are possible transformations we can do for a given tensor program that contains multiple loop nests, buffers, and computation. The most common transformations we can apply to this kind of tensor programs is what we call a loop transformation. In this particular case, we are using a pseudocode to demonstrate what are possible transformations we can apply to a primitive tensor function. So here's a code example for adding two vectors together. And we're going to do some pragmatic transformations. In this case, I'm going to say that I'm going to obtain this loop. I'm going to call split to split into two loops. Okay. So if we are going to run this, of course, this is a pseudocode, so it does not directly correspond to a directly runnable case. But it will give you a hell of an idea of what kind of transformation that we can apply on those tensor programs. So if we run this, we're going to get another variant of program. So you'll find that instead of x in here, we're going to get x2 and xi. This particular iterator is being split onto two possible iterators, and we can use this same expression to recover the original x. Right? So this is called loop splitting. So we'll be able to split loop iterator onto. Of course, if we only look at loop splitting, it's not so interesting, right? Because effectively we are doing same kind of iteration in over one directions. But loop splitting is kind of like a basic building block for what we can do next in the next few steps. Okay. So after we do the loop split, the second thing we can do is we can go and reorder some of the loops. In this case, we get this original program, and assume that I want to reorder the two order of looping here. It's going to give us the code on the left on the downside. What you can find that only difference, we're going to reorder the iteration of these two loops. For this particular add addition example, actually, these two programs are equivalent to each other, except that the iteration order is slightly different. And actually, depending on how we are going to the underlying implementation, these two variants could have like a different kind of execution efficiency. So we can find that this kind of program transformations is an effective way for us to get different variants of programs without having to directly express them on directly write them down. You will be able to directly use a transformation primitive to transform among them. And there could be more pragmatic program transformations, but these are kind of like two examples of possible pragmatic transformation that we can do. And finally, if you are familiar with GPU, what you can do is I can try to bind some of these iterators onto the GPU thread blocks, and then eventually you will get something like a GPU kernel that that allows you to run this particular code on GPU. Okay. So to come back at a high level, what we can find is that in order for us to be able to optimize a primitive function, we will get these tensor program abstractions that allows us to represent the loop nest computations as well as multi-dimensional buffers. We'll get a set of transformations that allows us to transform this code on the left-hand side, and eventually through these sequence transformations, it's going to give us another code that implement the same purpose, but likely depending on your implementation, it could be more or less efficient. And this is a great way for a machine learning compiler to be able to explore possible kind of optimization transformation that we can do on a target environment. Okay. Of course, we cannot arbitrarily transform any program. For example, if I'm going to change my program slightly onto this one, that where B kind of is dependent on the iterators of of a different loop domain, of a different loop location. So in the previous program, regardless of what XO and XI are, these computer statements are going to execute independently from each other. But in this particular case, if you're going to reorder this two, you'll find that the program is no longer equivalent to the previous one. So in compiler, this is called loop carry dependency. It means that if I'm going to do loop iterations, like one iteration, second iteration, and third iteration, there could be some dependencies that among those loops. In this case, because the B is going to look ahead, look at value that's ahead of its XIX iterations. It's going to cause problems if we're going to reorder this too. That's why we cannot directly use. Well, there are two approaches here. So first, one kind of approach is we can go and analyze the program, really try to discover hey, there's these dependencies that so that we cannot do this transformation. There are a class of works that go and do that, and in certain extent, it's also very useful to go through that approach. Another approach that we can take here is we want to try to add extra information in a tensor program abstraction so that we can avoid such kind of transformation. So we'll be able to discover that, hey, in this particular case, it's not something we want to transform, but in most of the cases we're interested in don't have this kind of loop carry dependencies. In most cases, in a lot of dimensions, because of the nature of tensor computations, we can perform a lot of them in parallel. So we kind of really will benefit us to have that kind of information. So coming back to the tensor program abstraction examples we listed in the beginning, one of the key things to highlight in here is that this is called TVM script, so it's a way to express tensor program in a Python AST. And then in this particular case, it looks like a Python, but there's additional annotation in here that says that I'm going to have a VI, which is an iterator that corresponds to an iterator of length 128. And in this case, I'm going to assign I to VI, but I'm also going to assert that, hey, this is an iterator, and my requirement for the iterator is that they have to be here spatial means that it's spatially independent. So if we have like a two-dimensional output matrix or output computations, we have like two spatial axes. And the idea is that for any iterator locations, like if I choose VI to be 0, or if I choose VI to be 1, and if I execute in arbitrary order, they can be executed without any dependencies among each other. So this kind of like is additional information that we add in a tensor program abstraction that can help the system to be able to reason about this information and leverage them to be able to do optimization. For example, if I know that, hey, these particular computations only contains spatial iterations that are independent from each other, then there's a great degree of freedom that we can go and parallelize most of these iterations, either through GPUs or through CPU thread pools. Okay. So we've talked a lot about tensor program transformations and what a tensor program is. Now, let's start to try to do some real code examples and see what it really looks like in a machine learning compilation framework. Now that we have talked about the tensor program functions and abstractions, let's start to try to see what are the possible things we can do if we want to try things out in action. So today we're going to do a quick walkthrough of tensor program and tensor program abstraction and tensor program transformations on a real machine learning compilation framework, TVM. For the particular purpose of this course, we are going to be using some of ongoing developments that are not yet upstream. So we'll provide a packaged version for MLC in particular, so that we'll be able to talk about some of those connections when we are building those abstractions together. And some of those additional features will also become part of TVM in the near future. Okay, so to begin with, one of the things that that we want to do is we want to be able to construct a tensor program and transform them. So in specific in here, what we are going to do is we are going to import. So the first step we're going to call pip install mlc-ai nightly that gives us a package that contains all the necessary dependencies that are needed for this particular course. And then in here, what we're going to do is I'm going to import tvm. And in this particular module, what we're doing is we're trying to use a feature called tvm script that tries to take a tensor program and trying to convert them onto an in-memory representation. In this case, it's my module. Although this code looks like a Python code, it's not exactly a Python code that runs on Python interpreter. It's a code that we kind of leverage the Python AST, so we're embedding the tensor program abstraction in Python, and we'll be able to also take actions on them, like building a runnable module that we can execute later. Okay, so once we have this have these modules in place, there are a few things we can do with it. For example, the first thing that I will do is I will going to check the type of my module here. And if I'm going to run this, it's going to tell me that this is of a type of IR module. So in this case, IR module is a container that it's a data structure that we use to store a collection of tensor functions. So this is going to be also in the future lectures, we're going to come back to this concept of IR module. Effectively, it contains a collection of functions, right? So in this particular case, it only contains this main function here. But in other cases, in the future lectures, may contain more than the main function itself. Okay. Once we have this IR module, there are a few things we can do with it. Of course, in this case, we don't have to exactly inspect what it is because there's already this declaration here. But in other cases, if you get a module, then you don't know. For example, if I'm getting a module, I'm going to transform it. I don't know what it is. Then what I can do is I can try to type type of sorry, not type. I can try to print out a script function here, and what it's going to do is going to convert that back into tvm script format. So you can find in this case. Roughly, this printed out code looks exactly the same as coding here, with a few additional information. Like if you look at the code below, it contains information like the reads and writes. So these are annotation that annotates for this particular compute block. It's going to read the corresponding regions of A and B and write on the corresponding region of C. These are informations that can be helpful for us to go and run transformations of the code. Okay, so another thing that we can do is, we talk about tensor program abstraction and how do we transform it. So the next thing that we can try to do is, can we go and try to transform this tensor program? In a particular case, can we go and transform this IR module? To do that, we're going to need concept called schedule, which is a helper object that helps us to be able to transform a module. So what we're going to do is we're going to create tvm tier.schedule, which is an auxiliary helper class that helps us to go and allows us to do operations on it. If I directly do schedule the module, it contains a current state of transform code. So right now, if I directly do script module.script, it is the resulting module. So you can find that this is going to be exactly the same as the original one. But as we start to try to change things can become a bit different. So the first thing we want to do is we want to be able to split the loop, just like in a slide example. So what I can do is I'm going to first get a block. So I'm going to do schedule.get block of C. This is going to give me that block. And once I get the block, I can get the corresponding loops. So I can say I equals schedule.get get loop and of that particular block. And in this case, because I only have one loop, so likely it's going to return array of length 1. I'm going to unpack that on y. Okay. Oops, there's no get loop. I guess it's get loops instead of get loop, because we can get many loops from here. Bingo, that's right. So once we get loops, the next thing that I can do is I can do schedule.split. Now we're going to ready to split the loop. So I'm going to do split the loop, and we can see factors. So on this particular example, let's assume that I'm interested in what do we do? So I'm interested in splitting into a factor of 4, right? Just like what we did in the lecture. So in here, what I'm doing is I'm going to do things like I0, I1 equals, maybe I'm going to split into even more loops in here instead of 2 loops. So and I2. And I'm going to split it in this way. Okay. So after these operations, and let's try. I'm going to do print of schedule.mode.script again. You're going to find that this particular program is different from the previous programs. So you can find that this is first of all, there are 3 loops in here that correspond to I0, I1, and I2. So if you look at this line in here, they have 3 loops, right? I0, I1, and I2. And secondly, and if you look at original one, right? Original loop is length 128. The second thing is you can find that in terms of loop length is 448, right? So this is because this corresponds to the 4 here, this corresponds to the 4 here, and 8 is automatically deduced because 128 divided by 4, and 4 times 4 is 8. Okay. The third thing is that the iterators are mapped correctly, right? So the new bi equals I0 times 16 plus I1 times 4 times I2. So after this operation, you can find that the schedule.mode.script gives you a different tensor program that is equivalent to the original one. What we're effectively doing while we transform the program by splitting the loop. Okay, we can do a few further steps besides loop splitting. For example, another thing we talk about in the lectures, we can do loop reorder. So we can do things like reorder. So I want to reorder I2 and I1, these 2 loops. And after reordering, let me try to print out again. And you will find the change is quite subtle, right? You have like I2 and I1 instead of I1 and I2. So the order of the loop get changed. And we can even do some further operations. Like for example, one of the things that was quite typical is we want to be able to parallelize on the outer loop. So we can do things like parallel I0 in here, and then try to print out the code again. And you'll find that the outer loop here becomes a parallelized loop. Okay. So what it shows you is that this ability for us to be able to construct a tensor program abstraction and using this schedule, right, as a tool for us to be able to interactively transform the tensor program to different states. And these transformations will help us to get to some of the final optimized program. There are more examples on the, so you will be able to find the code example on a notebook being provided. There are more examples that you can try out, including how we can go and construct these tensor program functions using expression DSL, as well as how can we take that and further try and do some optimizations for the matrix modulation code. So one final thing we can do is we talk about how we can transform the code, right? But effectively, after transformation, we still want to be able to turn them into executable form. So in order to do that, what you do is you do things like rt mode equals tvm.build. So the build function is going to take IR module on the left-hand side. And in this case, I'm going to specify target equals LVM, because LVM is a target that we are going to use on CPU. And so once you compile, so this is a bit like compile function. It's like invocations of a compilation that takes in a module which you already transformed. So if you feed in the module of schedule.mode, it's going to compile something that leverages things like parallelizations on our side. If you are going to feed it into the original module, then it's going to be the code that doesn't leverage parallelization. Right? So once we have that, we'll be able to get a function out from the runtime module. Main in here. And then, so in this case, this function is what we call runtime pack function. So this is a type that in TVM is used to represent a function that we can go and run executions on. Okay, so we will be able to invoke this build function in Python shortly. So the same we can do, we can say a equals tvm.nd.array, and we want to construct data from NumPy. So I'm going to construct it from NumPy here, and equals load 32, and let's say b I'm going to do once, and then okay, b type equals so these two will construct two arrays that we can use as input. Here's array A, and here's array B. And let's also construct an output array. C equals tvm.nd.array. The reason that we want to construct the output array as well is so that we simplify the burden of a lower level tensor primitive function. So we only need to, they don't need to worry about computations without worrying about like a shape data allocation and so on. Okay, so we're going to construct this array and of d type equals 32. Now we have these three arrays. What we can do is, let's see. Okay, so I think it is because the shape is expected to be a tuple. Now we have these three arrays. What we can do is we can go and try to run it through a function. Run it through function A, B, and C are the three arguments that we run. And then finally, if we go and check the result of C, you'll be able to find out that actually this particular function executes that code correctly. Okay. So what's happening behind the scene of this build is that we are going to take this function of, again, we're going to take the schedule.mode.script. So what's really happening in build is Effectively, we're going to feed in this module onto a build function that gives me a runtime module, which contains a collection of things. And among them, right, they contains this particular function in here that I can go and invoke. And this particular function kind of implement this particular set of tensor program that is describing here. So a typical MLC process, what we can do is we can take in an existing tensor primitive function in the tensor program form, and we can run a set of transformations like loop reordering, splittings, and parallelization and other transformations, and then call build function to get the corresponding runnable functions that we can run on the operators of interest. So this is kind of like an overall flow of tensor program abstraction and how we can leverage tensor program abstraction to do program transformations and optimizations. So you'll be able to find this notebook on the course website, and it contains a few more examples you can try and play, and hopefully you'll enjoy the first attempt here. Okay, so come back to the summary. In today's lecture, we have talked about two things, right? First of all, we talk about the concept of primitive function and how it relates to the overall executions of end-to-end model execution. And secondly, we talk about tensor program abstraction, which is an effective way to represent primitive tensor function operators. The key elements of tensor program include multi-dimensional buffers, loop nest, and the combinatorial statement. And one of the key in here is to enable us to do program-based transformations that allows us to optimize tensor programs. And in those cases, the extra structure inside a tensor program abstraction can help us to provide more information to enable such kind of transformations. Of course, today's lecture does not cover all the possible optimization transformation that we can do on a tensor program. It's just to give us a first step towards the tensor program abstraction part. In the next lecture, we're going to talk about how we're going to stitch everything end to end, and then we're going to come and iterate to bring more advanced optimizations onto the tensor programs and end-to-end workloads as well. Thanks for attending today's lecture, and I will hopefully see you all next week.